Okay, so once again in class I had some technical difficulties and was unable to record our lecture. But what we did was this problem where we had a time-dependent force given here with F in newtons and T in seconds. Notice it's time-dependent, is exerted on a 2 kilogram object initially at rest. First question was, at what time will the object be moving with a speed of 15 meters per second? And we found, the time is equal to 3 seconds. So t is equal to 3 seconds. The final position of the object when its speed is 15 meters per second is 18 in the x direction minus 9 in the j direction, and that's all in meters. And lastly, through what total displacement has the object traveled at this moment? And that's basically finding the magnitude of this vector, this position vector, and that was 20.1 meters. So then the question arose, well, what does it mean for the object to have gone 20.1 meters? Well, that's its displacement, but how far did it actually travel? So the force vector, notice in the x direction it's unchanged, but in the y direction it gets larger and larger. So initially, my first initial force, F1 maybe you want to call it, looks like this, and then sometime later it's a little bit steeper in the y direction it gets greater and greater slope down and so on. So we would expect our object to follow somewhat of a curved trajectory, whereas, so if it started here, initial position, here's its final position, where all we calculated was the net displacement here. So the question arose, what's the actual distance that my object traveled? Well, it turns out we can figure that out. So in order to find the length of this line here, I basically want to break it into little components that I will call d sub L. D sub L is a vector, and it's made up of a little piece in the y direction, I'll call that dy, and a little piece in the x direction, d sub x. Those are also vectors, right? dy points down, dx points to the right. So for completeness, that's what it looks like. And then once I get all of my little dl's, I can, what's going on here? I can add them all up, okay? So the first question is, how do I get my dl's? So there's a couple ways to think about it. Well, I know that dl is equal to the square root of dx squared plus dy squared, right? This is just Pythagorean theorem. So that's fine as long as I can get dx and dy. I found earlier that my position vector r is equal to 2t squared in the x direction minus 1/3 t cubed in the j direction, or if you prefer the notation, 2t squared comma negative 1/3 t cubed, right? So here's my x position, here's my y position, both as functions of time. Then I can say x position is 2t squared. So dx is equal to 4t dt, whereas y is equal to negative 1/3 t cubed, and dy is equal to negative t squared, right, take the derivative of that, dt. Now I can plug these two things, right here into my dl expression at the top. dl is equal to 4t squared dt squared plus negative t squared squared dt squared, all to the 1/2. Let's simplify this. Well, this is 16t squared. Now I have a dt squared times both terms, so I can do this. Let's pull that out. So negative t squared, that's positive t to the 4th to the 1/2 times dt squared to the 1/2. I can do that, and then I can cancel these two. So this is just 16t squared plus t to the fourth, all to the 1/2 power times dt. So that's good, but there's actually another way we can think about this. So another way requires another color, and that is from the velocity. So I also found earlier that my velocity, which is a vector and also a function of time, is equal to 4t in the I hat minus t squared in the j hat. And I can rewrite that as 4t in the x direction minus t squared in the y direction. So this is my v sub x, and here we have my v sub y, but I know that there's a relationship to position and velocity. Recall our original definition of velocity was simply the time derivative of the position. So I can rewrite this, solve for dx. dx is equal to v sub x dt, or here 4t dt. Likewise, v sub y is equal to dy dt, the time derivative of the y position. Rewrite this in terms of dy, it's v sub y dt, and that equals negative t squared dt. Well, already I'm starting to see that these results are going to give me the same expression for dl. So dl is equal to the square root of this thing squared plus that thing squared, which is really just written here. So I'm just going to rewrite it again. 16t squared plus t to the fourth, all to the 1/2 power dt. Okay, so now all I need to do, if I agree that this is my correct result, is now I need to take the integral. So let's do that. Okay, so now my total path length is equal to the sum of all of these little pieces of dl. Well, that's equal to the sum of all of these little pieces, 16t squared plus t to the fourth to the 1/2 power dt. From here, I can pull out, there's a t squared in each term, and since I'm taking t squared to the 1/2, that's t squared times 16, oops, no more t, 16 plus t squared all to the 1/2 dt. Now from here I did a u substitution, so let u equal the stuff in parentheses, 16 plus t squared. That means du is equal to 2t dt, or I can rewrite this, oops, that squared is not supposed to be there, excuse me. All right, because I pulled out a t squared here. Here I pulled out a t squared and t squared. T squared to the 1/2 is just t. So let's see, where are we? Good. Over here, 1/2 du is equal to t dt. Here I have a t dt. So that becomes the integral of this thing is u to the 1/2, and t dt is 1/2 du. Now, what are my limits of integration? Well, when I'm integrating over time, I'm integrating from 0 to 3 seconds, because that's what I'm looking at. U, it's a little bit less clear. I have to plug in some numbers here. But this is something I can easily take the derivative of. The integral. So I pull out the 1/2. This becomes u to the 3/2 times 2/3. Right? Yeah. Okay. And then, like I said, I'm not sure what my limits are of integration, so I'm going to plug back in this expression for u. So this becomes 1/3 times 16 plus t squared to the 3/2, and my limits are from 0 to 3 seconds. And if I plug this into my calculator, it's not too hard to do, I end up with 20.3 repeating meters. Well, it's satisfying because it's not, definitely not wrong, right? It's not smaller than 20.1. It is something that's bigger than 20.1 meters, but it's still kind of unsatisfying. I would have expected something quite a bit larger than that. So I thought about the resources that I have available to me, and I remembered that I have Wolfram Alpha. So for those who don't know Wolfram Alpha, it's this free math program that does all kinds of amazing things, including a parametric plot. So in order to visualize what exactly is going on in this problem, I decided to use Wolfram Alpha to plot this. So the x component of my plot is 2t squared, right? That's my, you can see I've done this before, I practiced. That's the x component of our position vector. Our y component is a negative t cubed divided by 3. My upper limit is 3, my lower limit is 0, and the variable is t. Okay, so now what does that equal? Let it think for a moment. I don't know what that is. There we go. Here's my parametric plot. Here's my x component from 0 to 3. Not sure what the v is from minus pi to pi, but regardless, you can see that this line that's actually not very curvy. And if I had a straight vector from my origin where I started to my endpoint, this curved line is not going to be significantly longer than the vector that points directly from where I started to where I ended. So I felt a little bit better about my result. And if we scroll down a little bit more, we see that Wolfram also calculates the length of this curve for me. That was nice of them. Right, here's the same integral that we had set up. And they got the same result of 20.333. So I think this is the correct answer, even though it was a little worrisome at first. But yeah, so that's how we would figure out how far we actually went. Hope you enjoyed it. Enjoy your week off next week. And I will post screenshots of the lecture as soon as I post this one. Okay, bye-bye.